So this talk is going to be about AD semantics, pitfalls, and the level of abstraction. And before I go into the actual content of the talk, I want to say a few things about the things that I'm going to talk about and how we got to this point. So this is work in progress. We are working on a review paper where we are trying to collect situations in which AD fails or breaks or behaves kind of funny and unexpected, so that users who are perhaps new to the field or not so new to the field can sort of look at this thing and figure out all the dangerous patterns that they should avoid in their code, and hopefully get the results that they're expecting. This is not just based on my ideas. There's a couple of people that contributed ideas. Billy right here, Hashita Menon, Paul, Bruce Christensen, Laurent Hasquet have helped a lot with discussions on this. So how did we get to this point, right? If we write papers about AD, or someone asks us what is AD, we usually come back with some version of, well, AD differentiates computer programs, and then we like to sort of separate ourselves from the competition and say, well, unlike symbolic differentiation, we can handle large computations with loops and branches and all these things. And then unlike finite differences, which of course nobody likes, AD is accurate. So that's great. Except, of course, as we've seen just a couple of talks ago, except if your code has parametric integrals. If you have parametric integrals, then there's this thing you need to do, because otherwise AD gives you wrong answers. Or except, of course, if your code has linear solvers, because obviously you shouldn't differentiate through linear solvers. There's a linear solver fix that you should be applying. But then AD is really safe, right? Except, of course, if you have fixed point iterations, obviously you shouldn't differentiate through fixed point iterations. That would be kind of bad. So don't do that. There's a fixed point iteration fix due to Bruce Christensen, and of course that's what you should be using. Or if your code has Monte Carlo sampling, the list goes on. There are all these kinds of situations, and that's where we sort of started getting scared. It's kind of weird that we say AD differentiates programs, but then there's this sort of seemingly random collection of situations where, for some reason, AD doesn't give you the answer that you were expecting, right? So then we asked ourselves, what's going on here, right? Does AD just randomly break for certain algorithms and not for others? Or can we somehow make sense of the failure modes and maybe identify sort of a finite list of categories of problems in which all of these sort of seemingly random situations fall, so that we can tell our users, if your code does this, then it's going to be fine, but if it does that, then it's not going to be fine, right? Instead of just having this ever-growing list. Some of these items on the list, for example, the parametric integrals, are actually quite recent discoveries, right? So it's not just a long list, it's also a growing list. So it would be really nice to make sense of all this. And so here, I'm going to try and make sense of this. But before we talk about how AD fails and what are the problems with AD, maybe we should first start asking ourselves, well, what does AD actually really compute, right? What do we expect? And one good way to start with all of these questions is, of course, to look at Andreas Grivank and Andrea Walter's classic book on AD, and just see what they say about the purpose of AD. So I'm going to quote this. Frequently we have a program that calculates numerical values for a function, and we would like to obtain accurate values for derivatives of the function as well. Now that's one of the few examples of an actual true statement, in that Andrea and Andreas were, of course, smart enough not to claim that this is what AD actually does. They just say this is what we would like it to do, right? So the question is then, of course, is this just wishful thinking, or do AD tools actually compute derivatives of some function that is implemented in a program? And so we are trying to now go through these various kinds of problems, and we've tried to categorize them into what we call here pitfalls. We have 4 pitfalls so far that we have identified that all the problems that we've seen fall into. So I'm just going to go through this list of pitfalls, and hopefully all the examples that you can think of that make AD break fall into one of these categories. I would always be happy to hear your examples. I'm also happy about to hear examples that don't fall into any of these pitfall categories, because then we need to invent a new category, and hopefully at some point we have an exhaustive list. So the first pitfall starts with the question, do you actually want the derivatives of that function? And just to give a basic example, I think this is a problem that everyone knows about, chaotic functions. Clearly, if you have a chaotic function, the derivatives are going to be kind of crazy, right? Because the sensitivity of the behavior of the system on the input parameters is going to be huge. But what if we don't actually want to have the sensitivities of the state of the system at any point in time, but maybe we're only interested in the time averaged behavior of the system? So in this case here, we have the Lorentz attractor with two slightly different input parameters, an R value of 27.9 and 28.0. Doesn't really matter what it does. The two behave wildly differently at any point in time. But if we actually look at the average, say the average x coordinate, averaged over a very long time frame, they don't vary very much with the R value. In fact, what we would expect for an infinitely long time window is that there's a smooth dependency of the average value with respect to this R parameter. And if we just take these two parameters and plot out the time averaged value up to some number of time steps here, then we see that it sort of nicely converges to some value, and the difference between R of 27.9 and R of 28 isn't that large. However, if we then apply AD to this time averaged function, and we're looking at the derivative of the time averaged value with respect to R, we're getting the second plot here, where we get exponential divergence over time. And I just want to point out this y scale here. So we are already at 10 to the power of 10,000 after we've done about, is that a million, 10 million? I can't count zeros. We've done a number of time steps that isn't huge for like a PDE-based solver in an actual application, but the derivatives just go crazy. And of course, if you had done this with double precision or single precision, you would have had nonce or infinite values long ago. This is all done with an arbitrary precision library. Kind of annoyingly, if you use finite differences for this problem, you do get something that converges to a finite value. And it actually converges after a while to a pretty good finite value. So in this case, even though AD gives you the correct derivative, and the correct derivative for any finite length time window does actually diverge exponentially, finite differences here gives you the more intuitive value, which is kind of similar to the value that you would have gotten had you only integrated for an infinitely long time, which of course you can't. Right. So of course the Lorentz attractor is not something that you want to deal with, but maybe you have a PDE solver, and maybe your PDE solver has some chaotic effects somewhere inside it, right? Maybe you have a little bit of turbulence, but you're only interested in a time averaged property of this. Sometimes these things crop up if you increase the grid resolution, if you switch from a RANS model to an LES model, suddenly you're seeing all these things. And even though the time averaged value that you're really interested in does depend nicely on all your input parameters, the derivative exponentially diverges, and not because AD is wrong, but because the actual derivative of that function grows bigger and bigger over time. But we don't actually need to talk about chaos, right? We can just have very harmless oscillations. So what I'm plotting here is the time averaged y coordinate for a cosine function. So all I'm doing is I have a cosine function that sort of oscillates over time, but what I'm plotting here is the time averaged value of that cosine function, which of course should converge to 0 if we just integrate over a long enough time window. Now we could ask ourselves, what happens if we differentiate that function with respect to the frequency? Because clearly if we change the frequency of the cosine function, the average value shouldn't change, right? We just change sort of the speed at which it oscillates, but we still should get a 0 average value. Unfortunately, the derivatives of that thing also don't converge, right? They sort of nicely oscillate between -1 and 1, and they never settle down. And again, this is not because of round-off. This is not because of truncation. We're actually computing the correct analytical integral of this, again, with an arbitrary precision library. And the correct answer is the derivatives just don't converge to the value that you would expect. The reason for that is in this plot here. So here we have the time axis, and here we have the frequency axis. And so as we go further in time, sort of the amplitude of that oscillation gets smaller and smaller, but the sensitivity on the frequency starts to oscillate faster and faster. Even though the amplitude dies down, we also compress the frequency, and the derivatives actually stay pretty much constant no matter what we do. So the function that I showed on the earlier slide goes way further than this, and it's kind of hard to plot this in a 3D surface, but that's basically what's happening. So, of course, also this example is very contrived, but there are many PDE-based models. You could think of anything, PDE-based fluid dynamics, climate. You have all these situations where you have periodic oscillations, and you're interested in some sort of time-averaged value. And I'm not saying that you're always going to run into this exact problem, but you should definitely be scared, and know exactly what you're doing, because the function might actually have very unexpected derivatives. And that wouldn't be an AD failure per se. It would just be that your function is weird. Again, annoyingly, finite differences gets it right. And in this case, that's because as your frequency goes up and the oscillations become more and more fine-grained, at some point they just drop under the step size of your finite differencing scheme. So finite differences fail to resolve those very high frequency oscillations and converge to the correct value, which is 0 here. OK, so that was the first pitfall, functions that sort of behave weirdly. But the next pitfall is then, do you actually want to differentiate at that abstraction level? Usually when we hear talks about raising the abstraction level or differentiating at a lower abstraction level, we hear these arguments mostly being made in terms of performance, software engineering, and all these kinds of things. But actually, your program could have different meanings based on which abstraction level you want to differentiate. And now here's a quote from Uwe Naumann's book, which is also nice because I think it's correct. It's sufficiently blurry. So it says, AD differentiates what you implement, which occasionally differs from what you think you implement. OK, we're going to refine that statement to try and make it a little more precise. But let's just look at abstraction levels for a moment. So let's say you have a program that implements sine of x. And Billy has shown some examples. I think we've seen other examples as well. The sine function might be implemented, for example, using a polynomial approximation. Or there's this clever algorithm called CORDIC, which basically allows you to bit by bit reconstruct the expected value. And you sort of get the guarantee that whatever bit you have constructed is going to be exact. So you can use CORDIC to basically produce results up to any precision that you want. You could have a lookup table, perhaps, or a lookup table followed by a Newton step. And then usually that at some point gets lowered down to some bit magic, right? Every computer program dealing with floating point numbers, at some point it boils down to just bits. We don't have real numbers. So if you just drill down deep enough in your computer program, at some point you will have inputs from a finite set, you have outputs from a finite set, and every program at a low enough abstraction level just becomes a step function with 0 derivatives. So clearly, the level of abstraction matters for when you're asking yourself, what are the correct derivatives of my function? Because on this top level here, the derivative would be cosine of x. On that intermediate level, well, the lookup table is already a step function, so that's a 0 derivative. CORDIC, I tried it with Tapenade. It's also 0 derivatives everywhere. The polynomial approximation, you could construct it in such a way. That's something that libc, for example, does on some platforms. It's actually a piecewise polynomial approximation that is bitwise exact. right? So there's not even an approximation per se going on. You get bitwise exact values, but it's a polynomial. If you differentiate that, you lose an order. If you differentiate it a couple times, each time you lose an order. So eventually, even that will get you, progressively poorer derivatives, but they will actually be correct derivatives of that polynomial, right? And then, 0 is the correct derivative of that bit magic that you did and the lookup table. So the question of, what is the correct derivative for a program depends on the level of abstraction at which you're applying the AD tool. So here's, our first fix to that Naumann quote. AD differentiates what is implemented at the abstraction to which you apply AD, which occasionally differs from what you think it is, right? And that's your choice. Now, I want to note here, abstraction level doesn't mean language, of course. We've just heard MLIR. You could have various different abstractions within MLIR. Sign of X could be in C. The implementation in libc is also in C, right? So it's not really level of abstraction equals language. It's really about what are the operators in terms of which your AD tool operates. And if your AD tool knows that sign of X is an operator, then that's your level of abstraction, right? If you allow your AD tool to look into the implementation of sign of X, then whatever that code has inside, that's the level of abstraction. Okay. Here's another example. I will just very quickly go over this. We've had so many good examples of levels of abstraction and getting unexpected results. This is one that I particularly like. It's an iterative process to compute the square root of x using Heron's method, which is very old, very effective. It actually converges very fast. And what we could do is, well, if Heron of x computes the square root of x, we can just brute force differentiate through that and just see what we're going to get, right? And this is the picture that we're getting for square root of 2. So here we're plotting basically the initial guess on this axis here. So if we are guessing square root of 2 as our initial guess, Heron's method is going to return immediately without actually doing any iterations. And then consequently, the derivatives that we get from brute force differentiation are just going to be 0. So they're going to be orders of magnitude off from where we actually want to be. And then when we go into initial guesses that are progressively poorer, the method actually will do a few iterations. But the accuracy of your derivatives is always going to lag behind by maybe about 2 orders of magnitude compared to the primal that you're getting. And if we just go on to plotting here on a log scale the initial error, so if we have an initial guess that is within 10 to minus 6 of the initial, then we get this huge gap between the final error in your primal and the derivative. And then we have this sort of funky jigsaw function because, depending on how close we were to just needing another iteration or being fine with the current number of iterations, we might get a sort of acceptable derivative or maybe not. Right? And then there are plenty of other examples where the level of abstraction really works. And what I really want to argue here at the end of this pitfall section is all these fixes that we talked about, the fix for linear solvers, the fix for fixed point loops, the integral fix. I think these are not fixes per se, right? These are all just your choice to raise the level of abstraction at a particular point in your program. So you tell the AD about something that is now a new operator, and you allow the AD tool to just consider this whole thing as one operator and express derivatives at that level of abstraction. Then, this pitfall is a bit shorter. Do you actually want to differentiate that branch? At first, we thought this was the same as pitfall 2, because, again, it kind of interacts with what you implement in your program and what you might think you implemented. So here's an example, right? Very simple. F of x is x everywhere except at point 0. If x is 0, we're going to return 0. Now, this function really is equivalent to f of x is x, right? It's just an identity function. We've just arbitrarily chosen to put a branch here. In mathematical sense, this, it really doesn't make any difference. Of course, if you implement this in code, it very well might make a difference. This happens, for example, in BLAS and a few other routines. Maybe there's a fast path where if you know that one of your arguments is exactly 0 or is exactly 1, you might be able to skip parts of your computation and be done with it. The problem with that is then, of course, when you go into that branch, you get wrong derivatives, right? Because in that branch, the output doesn't actually depend on x. Even though the function is just an identity function, f of x is x, if you just happen to hit that null point, the AD tool thinks that it should be a 0 derivative, when really it should be a 1 derivative. And this is not a problem about discontinuities, right? The function is perfectly smooth. It's also not that the presence of branches itself is a problem, because on the right side here, I just allowed myself to modify the example a bit. So now if x is 0, we are going to return sine of x. And that's the same value. It's really equivalent. But in this case here, it just so happens that AD is also going to give us the correct derivative. But the second derivative will be wrong, and all the subsequent ones, right? So it's not really that the function isn't smooth or continuous. It's that the branch that you happen to run into implements a function that has the wrong derivatives. And so, extending that statement even more, AD differentiates what is implemented at the abstraction level in the branch that gets executed. Bummer. What about roundoff? We've kind of, I think some people alluded to that, but even more so, what about approximate operators? And so here comes sort of the next statement here. If we have just this example here, linear solver fix, we know works very well. Your primal does x equals solve of A and B. So A is the matrix, B is your right-hand side. We know this is equivalent to just saying x is, at least mathematically, right? You wouldn't code it like this. It's equivalent to saying x equals A inverse times B. And you could choose to implement this as a CG solver, which then, of course, would take an initial guess x0 here. And just doing AD on this, let's just assume that A isn't active, but the right-hand side is active. Pretty straightforward. But then you could ask yourself, and you should ask yourself, will the CG solver converge in both cases? Now, the matrix is the same, but your right-hand side is different. And also, do you actually have a good initial guess for xd0, right? You might have had a good idea about your initial guess for x0, but do you actually know what a good initial guess for this derivative value should be? Unclear, right? And so, here's another example that's slightly older now. We've shown this a couple of years ago. This is a CG solver applied to a Hilbert matrix of size 11 times 11, which is extremely ill-conditioned. We actually know that CG, because it's a matrix of size 11 by 11, CG should converge and give us the exact solution after 11 steps. But it so happens, because of roundoff, that it continues to improve on its result way past that. But even if we use the linear solver fix, so this is this sort of light blue line here, we don't actually get accuracy as good as the primer. And even worse, if we brute force differentiate through it, then the result is totally wrong. And so, extending on this a little more, I think a true statement is to say AD differentiates at your abstraction level in the branch that gets executed, and assuming that all the operators that you encountered at the chosen abstraction level actually work precisely, right? And that means you don't have roundoff error. And if you have sine or cosine, for example, it's implemented sufficiently exact. If you have linear solvers that you treat with the linear solver fix, it's exact enough, etc. So, a couple of takeaway messages here. 3 parts. Even if we had a tool that could handle all your language features, and you didn't care about performance, or maybe Enzyme just became magically very, very fast and very, very mature, even then, it's not a good idea to think about AD as something that can just differentiate your program like a black box, right? You really need to understand the function that you're actually interested in, the function that you've implemented, the function at the level of abstraction, at all the branches, and so on and so on. And you need to be able to sanity check the derivatives that you get out of that tool. So if you want to be very cynical about that, you could say AD should only be used by people who know the derivative of their code. That's really sort of the level of at least in a dialogue with the AD tool, you should be able to figure out, yes, this is what I would expect. It's not a black box tool, and I don't think it ever will be. It's not a question of tool maturity. It's just not how AD works. who's responsible for all these problems and all these pitfalls, right? We've seen, we could have weird functions, weird abstractions, weird branches, inaccurate operators. I postulate, and I'm happy if you disagree, please tell me about it, that for the things up here, the responsibility will be mainly by the user. Right? The user tells us what function they want to differentiate, and the user tells us what abstraction level they want to apply AD at. They choose to apply AD either at some DSL level or at IR level, and because the function has different meanings and at all of these levels, and they're all correct in some sense, I don't think that there's going to be a good technological solution that will prevent users from shooting themselves in the foot that way. Maybe we can, design languages or design tools that discourage dangerous patterns, but at some level, it's always going to be user choice. Then as we go down here with the branches, you could imagine some tool or some method. There are actually methods that also look at neighboring branches. I don't think there's any method that scales to an application code, PDE-based solver kind of thing. But at least there are ideas out there that would allow us to detect if we're doing something dangerous, if we're maybe in a branch that's only defined at one point and we're really near to a switch point, and that might change the derivatives. So it's possible that there are tool-based solutions for this. And then the operator accuracy, I think, is something that, potentially, if we get better at doing round-off error estimation, if we instrument the AD code in a way that, maybe it warns users if they're using some of the operators in their derivatives at input points that are known to be problematic, there's maybe some things we can do. And the last part of the takeaway message, which is kind of why I'm really happy to present this here. Enzyme is really special about this, and not in a good way. Right? And I say that even though I'm a big fan of Enzyme, but a unique challenge that we have here is that the user-facing API at which someone says Enzyme autodiff and the level of abstraction at which the AD engine actually operates, they are different. Right? So during that lowering from Julia or C or wherever the user might have called Enzyme to the point that it got into LLVM-IR or MLIR, it doesn't really matter, maybe the semantics of the program have changed. And when people develop lowerings from one level of abstraction to another, they usually care about preserving the functions in a certain way. But we've seen examples where, even though the representation that you get is bitwise exact, arbitrarily exact, your derivatives could still be arbitrarily wrong, depending on how the function is expressed. So AD has this sort of unique failure mode, where you can't really blame the user for not understanding the semantics of their program, because really what they should have understood is the semantics of the LLVM-IR at which Enzyme operated. So, who's at fault or who's responsible for fixing this? Right now, I think the mode is we're waiting for bug reports, and then we play whack-a-mole, and maybe that's the solution, right? Maybe that's the only thing we can do, and maybe the number of distinct situations in which these things happen isn't that large, so maybe that is the best solution. Maybe there's some way to automatically check if the derivative semantics changed during lowering. I wouldn't know how, but maybe. Maybe you could convince the front-end developers to be aware of derivatives and not do certain things, or tell Enzyme about custom functions that should be used. I don't really have a good answer to this, but here we go. Questions, comments? Now or by email later. And we have a question or comment.
Okay, let's thank the speaker first.
Thank you. That was a very good and entertaining talk. The last point about AD derivative language of front ends to Enzyme, I think you hit the nail on the head. The front ends really need to provide a level of abstraction in which the user can define their rules so that they can raise themselves the level to abstraction to what they want through rules, as an example. But because otherwise you run into That's really the part you can control, and then everything else, kinda you would say, okay, language semantics you need to get right. Enzyme needs to get the language semantics right and correct. But well, I don't know what the right derivative is for your linear solver as it is expressed over LVMIR.
Right, and I think scalability is really sort of the key point here, right? Because Enzyme is supposed to be sort of language agnostic at some level, so you definitely don't want to go into the business where you make it your job to detect in the IR that this piece of code looks like it could have been a cosine function in Julia or something like that, right? It needs to come from...
We already had encountered this to our enjoyment multiple times when the Julia core started implementing more and more of the pure math functions in Julia itself.
Yeah.
And then suddenly you're like, whoa. Why wouldn't you? It's the exact same code that is running in the end. But then Enzyme was like, well, none of this makes sense, right? And so adding the understanding and the language semantics, but allowing that the user can extend that is, I think, crucial.
Yeah, and sort of raising awareness that people, when they lower stuff, they shouldn't just make sure the function does the correct thing, right? So Enzyme just needs to become more popular so that people actually take care of that kind of stuff.
We are working on that.
Yeah.
Other questions?
Yeah, so I'm curious about your take on making, say, linear functions as part of the abstractions that we use for derivatives, because there's a sense in which you can think of derivatives as linear approximations of functions. If we had linear functions, as a building block,
I'm sorry, I can't
could that solve some of the issues?
I can't really hear that. Let me just come closer, and then I'm going to repeat the question, maybe.
Yeah, I was curious about your take on making linear functions part of the abstractions that we use for AD, because there's a sense in which you can think of derivatives as just linear approximations of functions. So if we had linear functions as an abstraction, that could potentially solve some of those issues. I don't know if you thought about that direction.
So you would sort of ask users to provide a linearization for functions?
Or mark certain functions as linear, and it doesn't matter if those are implemented as lookup tables or in any other weird way. And the assumption would be that the linear approximation of any linear function is the linear function itself, regardless of how it is implemented.
So the user would provide a linear approximation to problematic functions, and then you AD through that approximation?
Yeah, you will need some building blocks, but it's kind of like an open-ended. I don't really have a solution to the problems. I was just wondering about if you thought about how linear functions as an abstraction would fit into your talk.
Okay, yeah, it's an interesting question. I don't know if people on this side of the room. Okay, so I think the suggestion, and I think that is more towards potential solutions to this problem, right? If users would give us a linear approximation to certain problematic functions, and then we would just sort of AD through those, right? Then we would get the correct answer. So I think it's a slight twist on custom derivatives, right? You sort of give more AD-friendly versions of your function and then let AD do its job. That could be added as a bullet point here. I think that's also an idea. Yeah.
Any other questions, comments?
So, in the sort of branchy part of the potential questions, I think there's earlier discussion that we had with Harshita, which tried to analyze when, in particular, those branches could cause a problem in this context of AD. And I think we landed a little bit talking about where if the branch itself is independent of, say, the active variable, like size 3, iterating through a list, it's not really problematic. But if it's a branch based off of the active or differentiable variable itself, then it can be problematic.
Yep.
My sort of generalization of this question for you is, do we think that there's a potential sort of like program space that we can define that sort of says programs within this space should not have a problem, or the converse of this, which is to say programs explicitly with this sort of behavior do.
Right. So I don't. Did the people in the back of the room get that? So I mean, so this is about the branching pitfall, right? Can we somehow identify a category of programs where we can say this is problematic branching versus some other category of programs where we know this is not problematic branching? And I think we definitely have categories. I just don't know if they're useful categories yet, right? Because they're not very sharp. So right now, anything with data-dependent branching or dependent on an active variable, I think is potentially problematic, which is pretty much every program that we really care about. So I don't know. Maybe you would want to detect that you're near a branch. I think one of the unique problems about the sort of branch pitfall is that the problematic branch is really just a single point, right? If that wasn't the case, then the derivatives wouldn't be wrong per se, right? They would just sort of necessarily in that branch, if it's more than just one point, if it's sort of a finite-sized interval, it needs to implement something that has more reasonable derivatives. You can't just drop all the dependencies. So maybe you need to look out for these sort of branches that are just at one point. The problem is, of course, that's not so easy because you could sort of trick your way into having a branch that only works for one point by using comparison operators in a creative way. Maybe you need to explore nearby branches and hopefully do that without combinatorial explosion. Yeah, but I mean, yeah, open question. And I haven't gotten much further towards getting a good answer compared to where we left off.
The example that you're showing right now is also particularly insidious because the compiler can look at the branch condition, propagate it in, evaluate sign constantly as 0, and optimize your program out.
That's right. Yeah, and then you would get different derivatives with enzyme
depending on
correctly.
If you're doing the AD before or after those kinds of optimizations.
Yeah, and maybe you would get the correct derivatives with enzyme. I mean,
whatever is the correct, right?
Correct. Yeah. So, I don't know. Yeah.
Yeah, we just need to find everything is interval arithmetic.
And I mean, the thing is like why I like this example with the sign of x and 0, right? We sort of started thinking, is the branching a problem, or is the discontinuity a problem or something? But actually the problem is the derivative of your branch, right? It's like it's kind of annoying. It's a very annoying example.
Okay, I think we can stop here. One quick question. We are running over time.
Yeah. Okay, maybe then I'll. No, this was a philosophical question.
Okay, then we can leave that for the roundtable discussion.
Is there one afterwards? Or?
Yeah, of course.
Okay, yeah.